Welcome to the video. Today we are trying to solve the problem equilibrium point. In this question, we are given an array. This array has only positive numbers and our task is to find the first equilibrium point. Now what does equilibrium point mean? It means the index of an element where the sum of all the elements to the left of it is equal to the sum of all the elements to the right of it. For example, in this array, that equilibrium point is this index where we have the element 5, because sum of all the elements to the left is 3 plus 1, 4, and sum of all the elements to the right is 2 plus 2, 4. Both are equal. Hence, this is the equilibrium point. So we have to return the index of such an element. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's begin. So first, let's just note down few key things. We are given an array. The array has only positive integers. We have to find the equilibrium point, the first equilibrium point. And what is an equilibrium point? Sum to the left should be equal to the sum to the right. Let's understand this with an example. In this array, this is the equilibrium point because sum to the left is equal to sum to the right. So if our solution was a black box, we are getting input as array and we have to return an integer, which is the index of the equilibrium point, as output. So our function signature would look something like this: int equilibrium point that takes input as an array and its size. Okay, let's begin. So if we have to think about this, how can we think in the simplest possible manner to solve it? We need to find the equilibrium point. So what we can do is we can take every element one by one in the array. And for every element that we have taken, we sum all the elements to its left and we sum all the elements to its right. And then we compare. If the sum is equal, we have found our equilibrium point, and if it is not, then we move to the next element. How much time complexity will this solution take? It will take big O of n square. Why? Because first, with big O of n time complexity, we will choose every element one by one in a loop. Now for every element, we are traversing complete to the left and complete to the right. That is why the time complexity is big O of n square. But is this the best we can do? Are we missing something or are we doing something inefficiently? Let's see. For example, when we are at this element 1, to calculate sum to the right, we sum all of these elements by traversing across the array. Now we pick the next element. To calculate sum to the right, we again traverse the whole array till the end. But is it really needed? If we know the sum from this point to this point, can we just not subtract 3 to get the sum from this point? And therefore, first problem is that sum calculation is not optimized. This is not optimized. Secondly, let's see. In this example, we know that we get the answer at 5. But let's say if this 5, we would have 6 instead of this 5. Now in that case, we will not get the answer at 6. Now does it make sense to move beyond 6 and keep trying to calculate sum left, sum right and compare? When we know that sum to the left is already greater, then every element that we add will anyways be greater. Right? So this is the second problem. We don't stop. We don't stop based on that we cannot find answer further. This is a very common technique when you are thinking about your solution approach. You should keep modifying your examples to think through the scenarios in which your solution will work. Therefore, edge cases here can be, for example, what if there is no equilibrium point? What do we do then? let's say we return -1 for that. What if there is only one element? For example, array is this. Then will this be considered an equilibrium point? What if there are two elements? Will this be which of these will be considered as equilibrium points? These are some questions that we will need to clarify with our interviewer. Okay, so now we know that simplest approach is definitely inefficient. So how do we think about it? We know one thing for sure. For equilibrium point, left sum should be equal to the right sum. Left sum should be equal to right sum. So what we can do is we can start summing from left and we can start summing from right of the array, right? And we hope that at some point in time this left sum is equal to right sum. And even that is not sufficient, because let's say at this point I and at this point j, left sum becomes equal to right sum, but there are multiple elements in the array. Can we say that this element is the equilibrium point, or this element, or any one? No, because sum of these when added to right sum may not be equal to the left sum. Therefore, we need two conditions. One is left sum is equal to right sum, and second, that j minus I should be exactly equal to 2. So what are we doing here? In every iteration, we are maintaining left sum and right sum. Now, in every iteration, we will either add an element from left to increase the left sum, or an element from right to increase the right sum. Now, let's say at any point in time, our left sum is lesser than what our right sum is. Now, in this iteration, should we add an element from the left or should we add an element from the right? Obviously, we should add element from the left, because we are hoping that we reach a situation where left sum is equal to right sum. If we are adding element to the right in this case, then it is of no use, because right sum is already greater. Therefore, in every iteration we will add the element from the side whose sum is currently lesser, and we hope that we reach this condition: left sum is equal to right sum and j minus I is equal to 2. If we meet these two conditions, we will get our equilibrium point. This is a very common technique. When we have to keep balancing both sides, we maintain two variables from the left, one from the left and one from the right, and keep adding element from either side depending upon the condition that we have to balance. We can use this in multiple questions. Also, another thing, what happens if we reach a situation where left sum is equal to right sum, but j minus I is not equal to 2? What do we do then? There is nothing to do, because we haven't found the equilibrium point yet. So we will just simply add one more element in the left and keep going towards finding our equilibrium point. Okay, now let's try putting our thought into algorithm. So we know for sure that we have to iterate, and in every iteration, what all will we have? We'll have something called as left sum, we'll have a right sum, we'll have an I, and we'll have a j. And that means we have to initialize these variables earlier before the loop. What will we do next? We will compare left sum with right sum. And if left sum is lesser, that means we have to add an element to the left. If right sum is lesser, that means we have to add an element to the right and move the pointers accordingly. And what if both are equal? If both are equal and our j minus I equals 2, that means we have found the equilibrium point. So we will return. And if they are not equal, then we have to continue our exploration and we'll use left sum to increment again and continue in the loop. Now, till when will we run this loop? We will run this loop till our j remains greater than I, right? Now let's try to see the working code for the same algorithm. You can find the link to this code in the description of the video as well. So First of all, here we take care of the edge case. If there is only one element in the array, we return that as the equilibrium point. Secondly, then we initialize our left sum and right sum variables. And then we also initialize our I and j pointers. We put our equilibrium point value currently as -1. That means if we do not find it, we will return -1. Now we iterate. And in every iteration, we compare left sum and right sum. And if left sum is smaller, we move I one place forward and we add that to the left sum. While if in the iteration left sum is greater and right sum is smaller, we do the same with right sum. And if both are equal, then we don't directly return the answer. We first check that if j minus I is equal to 2. If that is the case, that means we have found our equilibrium point. Otherwise, we just keep on exploring by incrementing I and adding an element to the left sum. To summarize, we first tried to understand the problem very clearly with an example. Then we thought of the most simple approach that we can come up with. We thought that we can take every element one at a time, and for every element we calculate sum to the left, we calculate sum to the right, and we check if that is equal. But then we realized that this takes big O of n square time complexity. So to optimize that, we thought that why don't we maintain a left sum and a right sum? And in every iteration, we try to balance the sums. For example, if left sum is lesser, we add an element to the left side. If right sum is lesser, we add an element to the right side. And then we keep checking if that is equal and we have reached a point where all the array elements have been covered to its left and to its right. We saw the algorithm for it and also went through the code. If you have any doubts, etc., please feel free to comment below the video, and we'll meet again in the next video with some other problem. Thank you for watching.